Good morning. Last time we talked about conditional probability, which again is the probability of B knowing or given that A has occurred. Today we're going to talk about the special situation where having information about A doesn't actually affect the probability of B knowing that A has occurred. So let's take a look at that in an example. So let's say we want to find the probability of getting heads on the first toss, heads on the second toss, given tails on the first. Okay, so we saw an example like this last time. In terms of, but last time we talked about it in terms of and, we saw something similar to this. With this conditional probability, this is the probability of tails on first and heads on second over the probability of tails on first. So B given A, we have A and B over the probability of A. So this is what we saw last time, something like this. Tails on the first and heads on the second. That probability is 1 out of 4. Right? There's only one way that you can get tails then heads. There are 4 possible outcomes. The probability of tails on the first is 1 out of 2. You flip a coin once, 2 possibilities, and then tails is one of them. And this is equal to just 1/2, right? If you just flip over the 1 out of 2, 1/4 divided by 1/2 is 1/2. But that's interesting because this is exactly equal to the probability of heads on the second toss. Right? Let me just draw this so we can visualize it. If we're just looking at the second toss, then we have, 2 out of 4 of these are heads. So in this case, the probability of B given A was exactly equal to the probability of B. And let me put a caveat in here that's going to be important. Again, we can only talk about conditional probabilities in the first place is if the probability of A is bigger than 0. You might need to look at your notes for the last lecture when we talked about that. That makes sense because you can't divide by 0. So that formula wouldn't work if it were 0. Anyway, if we have it like this then, what happens to the multiplication rule? Well, in this special case, the multiplication rule, which is the probability of A and B, is the probability of A times the probability of B given A, that becomes the probability of A times the probability of B. So it simplifies to this nice product. So what was special about this situation? So in this situation, if you flip a coin, what happened on that previous flip is not going to affect your next flip. In English, we might say that those 2 events were independent of each other. They didn't affect one another. And this motivates the probabilistic definition of independence. So keep a little bit on the board, so I'm just going to erase to here. So here's the definition. We say 2 events are independent if the probability of A and B, so it's the same thing as the probability of A and B, is the probability of A times the probability of B. Otherwise, the events are dependent. Okay, so important subtle caveat to that definition. Here, the thing that motivated the definition was an example from the real world of things that don't affect one another. Okay, that's motivating my definition over there. But in this example, where we actually started with conditional probability, we specifically said that the probability of A has to be bigger than 0. I'm not saying that here. Okay, so this is how I'm defining independent events, and it doesn't talk about the probability of A being greater than 0. The reason I'm bringing that up is that we're going to see later on that because of this, because I'm not saying that the probability of A has to be bigger than 0, that this is not exactly equal to our English understanding of the word independent. So what do I mean by that? So what I mean is that if two events don't affect one another, like in this example, then they're going to be independent. They will be independent. However, we'll see again at the end of this lecture, we'll see some examples where this breaks down, this English understanding of it breaks down a little bit because we don't have this piece over here. So we'll worry about that later, but the upshot, the summary, is that when we talk about independence, this is the definition. The definition is not, oh, two events don't affect one another. That's Englishy. The definition is that this is true. So let me start highlighting that in an example. And then again, later on, we'll see how the what weirdness can occur over here when we start looking at events which have 0 probability. Okay, so let's do a definition to really hammer this point home. So an example, 40% people swim, 30% play golf, 10% do both. So are the events independent? Okay, so give that a shot. Pause the video, try it. So hopefully you paused the video and gave that a shot. And again, hopefully you didn't start asking yourself, gosh, I don't know. I think if you swim, you probably will play golf, or if you play golf, you probably won't swim. Hopefully you're not taking that line of reasoning. Instead, use the definition. So, are they independent? Well, is 0.1 probability of A and B, is that equal to 0.3 times 0.4? The answer is no, so they're not independent. That is the definition of being independent. If, however, and this is the point I want to make, if, however, the two events don't affect one another, like in that initial point example, then that will lead to this, and you'll know that they're independent. So for example, with that in mind, you know that if you roll a die multiple times, those events are going to be independent. Right? Because if I roll a die once, if I roll it again, it's not affecting it. Because of that, the probability of B, given that A has occurred, is just going to be the probability of B. And it will look like this, so those guys will be independent. Let me also say that, you might ask yourself, well, why do we care if things are independent or not? It turns out that this idea, if events are independent, this is something that makes computations both theoretical and, let me just say, numerical, like something like this. It makes them way, way, way easier. And we're going to see that time and time again throughout the quarter. So I would say this is a very important concept that will be peppered throughout the quarter. Okay, so now that we have an idea as to what independence is. Let's prove result about independence. So if A and B are independent, again, when I say they're independent, I'm thinking about that definition. So if these guys are independent, then so are 1, A and B complement, 2, A complement and B, 3, A complement and B complement. So in other words, if two events have this property, then the event and the other guy's complement will also have the property. Complement of the event and that original event will have the property, and both complements together will have the property. So how do we prove that? Again, you don't want to be thinking about it in terms of, well, if these guys don't affect each other, then these guys won't affect each other. That's not a proof, and what we need to do is we need to use this definition somehow. So how are we going to do that? Well, let's draw a picture. And I'm going to draw a picture where these two guys happen to intersect, but the proof actually is going to be the same regardless of whether they intersect or not. What am I trying to prove? Well, let me start with the probability of A intersect B complement. And again, I'm hoping to get that to be the probability of A times the probability of B complement. So let me say that A over here can be thought of as the union of two mutually exclusive sets. Now, what the heck does mutual exclusivity have to do with this? Well, let me give you a minute before we see why that's going to be helpful. I'll give you a minute, pause the video, see if you can write A as the union of two mutually exclusive sets, and this is something we actually did several lectures ago. So pause the video. Well, hopefully you said that this is A intersect B, union, let's see, A, everything that's in A, intersected with everything that's in B complement. Right? Everything that's in A intersect with everything that's outside of B. Well, that's going to give us that stuff. Now, why might this be helpful? Because it might be helpful because this is the set that I'm playing around with, and I now have it somewhere. So quite frankly, if this were the first time I were looking at this proof, I wouldn't know if it would be helpful at this point. But it's always helpful to, almost always helpful to try and get that thing you're trying to prove somehow into the discussion. All right, well, those guys are mutually exclusive, so the probability of A is the probability of A and B plus the probability of A intersect B complement. Ooh, this is starting to look promising because I know something about that. Well, first let me do some algebra. This guy is the probability of A minus the probability of A intersect B. So I just subtracted. Then I know that A and B are independent. So this is the probability of A minus the probability of A times the probability of B. Pause the video for a second, see if you can finish the proof. All right, hopefully you said I can factor out the probability of A. And then 1 minus the probability of B is just the probability of B complement. Perfect. So I've now proven that if A and B are independent, then so are A and B complement. All right, so again, I'm not even talking about whether they affect each other or not. I'm just using the definition of independence. All right, so and to prove the other two, I'm not going to do these. It's going to be a similar proof to this first one, and this other one, a similar flavored proof where you just need to express using mutually exclusive events. So I'll let you guys just try that on your own. So let's do an example. So let's say you are a sharpshooter aiming at a slug. So you take 2 successive shots. I'm telling you, shots are independent. The probability that you hit it on the first shot is 0.8. Probability that you hit it on the second shot is 0.6. I want to know the probability that you make both. And the probability you make at least 1. All right, so give that a shot and pause the video, and then we'll talk about it. All right, hopefully you said making both. Well, these, you're told they're independent, so it's just 0.8 times 0.6. So the probability I make at least 1. Well, I'm going to do this 2 ways. One is the longer way and one is the shorter way. So if I make at least 1, then I guess I can hit and then miss, or I can miss and then hit, or I could hit and then hit. Now these guys are mutually exclusive events, so if I compute the probability of that, I can just add them up. So the probability of hit and then miss is just 0.8 times 0.4, because the event and the complement are independent by that last theorem. Same deal here. Plus miss 0.2 times hit 0.6 plus hit both 0.8 times 0.6. A funner solution, or more fun, if you're into proper English, the probability that I make at least 1 is, well, that's the complement of what event? That's the complement of the event that you don't hit any. So this is 1 minus the probability of hitting none. The complement of hitting at least 1 is that you hit none. 1 minus 0.2 times 0.4, and you're done. All right, that's with 2 events. 3 events, it's defined similarly. I'm not actually going to write this down because we're not going to use it at all this quarter. So if I had 3 events, this is true for the 3 events. So probability of A, well, let me write down part of it, the part that we're interested in. 3 events, the probability of A and B and C is the probability of A times the probability of B times the probability of C. So if 3 events are independent, that's true. Technically, as part of the definition, they're also pairwise independent. So in other words, the probability of, if we have 3 events, the probability of A and B will be the probability of A times B. Probability of A and C will be the probability of A times C. Probability of A times the probability of C, etc. But we're not really going to use that at all this quarter. So let's not confuse the topic. And let me just say that if you have more than 2 events, if you have n events and they're independent, you can multiply them. So as an example, if if you roll a die 6 times, what's the probability that the ith roll is less than or equal to I? So the first roll is less than or equal to 1, the second roll is less than or equal to 2, etc., etc. So give that a shot, pause the video. All right, so hopefully you said that's the probability of getting, 1 or less. That's that first roll, and 2 or less. That's the second roll, and blah, blah, blah. 6 or less. And by what we have up here, we could just multiply the individual probabilities. So we have 1 out of 6, that's 2 out of 6, that's 3 out of 6, times 4, times 5, times 6 out of 6. Let me also once again tie this back to something that we know. We can also think of this as a counting question. So if it's a counting question, the first one is 1 or less. Oh, there's one way I can do that. The second one is 2 or less. So counting, I'm using the multiplication principle. 3 or less, 4 or less, 5 or less, 6 or less. The denominator is the total number of ways I can do this. Well, I have 6 possible outcomes on the first, 6 on the second, 6 on the third, etc., etc. So 6 to the 6th on bottom. And again, we're getting the same answer. This one, I'm finding the answer by probabilistic argument for term by term, and here with a counting argument. A lot of times, I've mentioned this, there's more than one way to solve these problems. Okay, finally, I want to talk about the relationship between mutually exclusive events and independent events. And the purpose of this is to clear up what I was talking about at the beginning, which is we can't think of independent, we can't always think about it in terms of the English verbiage, in terms of how we think about independence, and we have to resort to this definition. So we'll see what that's all about. How are mutually exclusive and independent events related? So if I were, and disclaimer, this is what I thought when I first was introduced to this topic 50,000 years ago. If we think about independence in the English sense, which again we shouldn't be doing, then you would think to yourself, well, if an event is independent, it doesn't affect the other one. Well, mutually exclusive events, they do affect one another because if one event's over here and they're mutually exclusive, well, then the other can't be intersecting, it's got to be over here. So if I were to follow that line of reasoning, it doesn't seem like it's possible for two events to be both independent and mutually exclusive at the same time. However, that's incorrect. And it's incorrect following the actual definition. Okay, so let me give you an example of this. So I'm going to write ME for mutually exclusive because I'm going to be writing it a bunch of times. So I claim that you can find two events that are both mutually exclusive and independent. Again, think about that. From the English perspective, that doesn't make sense. But this is the definition, and we'll see that we can. So let's let event A be, so let's say I'm looking at Math 341 students, and a student identifies as female, and B, the student is a mummy. I claim that these events are mutually exclusive and independent. Well, let's see. Are they mutually exclusive? Well, the probability of, mutually exclusive. I just need to see if A and B have an empty intersection. Do they have an empty intersection? Yeah, so we have students in class who identify as female, okay? But this set is an empty set. At least I hope it is. It'll be a little scary. There are mummies out there. Well, if I intersect any set with an empty set, I'm going to get an empty set. So A intersect B is empty, so they are mutually exclusive. Are these guys independent? Well, they'll be independent if the probability of A and B is equal to the probability of A times the probability of B. So the probability of B is 0. This is some number. And the intersection is empty. So the probability of the intersection is 0. So yes, these two events are both independent and mutually exclusive. So remember way back when I said, our motivation for being independent is that the probability of that event A was bigger than 0. Remember with the tail flipping example. But I said in our actual definition, we don't even use that. Well, this is what happens when one of the events has a probability of 0. Things get a little bit weird and not completely intuitive. So once again, the thing you need to worry about is that this is the definition. Okay, so that's one example where they're both mutually exclusive and independent. Let me say that every possible combination is available. So what do I mean by that? So mutually exclusive and dependent. Let's say A student identifies as male. B student identifies as female. Are they mutually exclusive? Yes, because the intersection of those two sets is empty. Are they dependent or are they independent? Well, is the probability of A and B equal to the probability of A times the probability of B? Well, in this class, we have about, I'm not going to be able to know the exact numbers, but let's say it's about 2/3 and about 1/3. Well, the problem is the probability of the intersection is going to be 0 because A intersect B is empty. So those guys are not going to be equal to each other in product. Okay, so they can be mutually exclusive and dependent. How about not mutually exclusive and independent? Yep, that's possible as well. Let's do a card example. So you're going to pick a card. So I'll give you a minute, try to convince yourself why those events are not mutually exclusive, but they are independent. All right, hopefully you said that A intersect B is hearts. So this is hearts, clubs, hearts, diamonds. So they're not mutually exclusive. So are they independent? Well, the probability of the intersection is the probability of getting hearts, and that's 1/4. Quarter of the deck is hearts. The probability of A times the probability of B. Well, this is half the deck, and this is half the deck. So the probability of A intersect B is equal to the probability of A times the probability of B, so those guys are independent. And then finally, if they're not mutually exclusive and dependent, well, is there an example of that? Let's do another card example. Let's do hearts or clubs. And hearts is B. So again, pause the video, see if you can convince yourself that they're neither mutually exclusive nor independent, so they're dependent. Right, hopefully you gave it a shot. A intersect B is just hearts. That's not empty. So not mutually exclusive. Probability of A intersect B is just 1/4. Does that equal the probability of A, which is half the deck, times the probability of B, which is a quarter of the deck? Nope. So they are dependent. All right, that's all I have to say about independence. Independence is going to be an incredibly powerful tool, both in this course and especially if you take more advanced courses in either probability or statistics. And the idea is that it converts any and statement into a multiplication statement. So it greatly simplifies the computation. Thanks for listening, and I will see you guys next time.